Alright, so now Nick is going to try to pull the brick at a constant velocity across the table. And remember, if it's a constant velocity, it still is in equilibrium. And we're going to see what force is required for that. So go ahead and do that there, Nick. So keep it going at a constant velocity. And what force are you reading there?
About 6.1.
About 6.1 newtons. Alright, thank you very much, Nick. Okay, so for this problem it's very similar to the last one, but instead of seeing how much force it takes, the maximum force we can apply before it moves, we're seeing how much tension it takes to pull it at a constant velocity. And Nick told us that that was taking 6.1 newtons, which you'll notice is a little less than the maximum tension required to get it to start moving. So we'll come back to that in a minute. We're still going to have our weight going down on this brick. We're still going to have our normal force going up. And now we still have friction, but we call this Fk, and that Fk stands for kinetic friction, and we'll define that in just a second. But from our free body diagram, we can see very quickly that N has to equal mg, and this is the same brick we've been using over and over and over again, and so we know that that is 15 newtons. And then if we look at our forces in the x direction, we know that T and Fk have to be equal, because this object, even though it's moving, is still considered to be in equilibrium if Nick really did a good job of pulling it at a constant velocity. And we're going to assume and we're going to say that he did. So as long as you're not speeding up or slowing down or turning, you are still in equilibrium. And so the tension and the force of kinetic friction are equal, and they are both going to be 6.1 newtons. And so for this problem, we're actually going to calculate the coefficient of kinetic friction. So where static friction was a force that resists surfaces sliding past one another and they're not moving, someone's just like trying to slide them past one another, kinetic friction is a force that resists the motion of surfaces that are sliding past one another and are actually moving in relation to each other. Okay? And the equation is very similar, except this time we don't have a max. It's just Fk equals mu k n. So Fk is equal to the coefficient of kinetic friction times the normal force again. So once again, the force of friction depends on the quality of the two surfaces, how smooth or rough they are, and how hard the surfaces are squished together. But this time we don't have a zero up to a maximum value. Fk will be a constant for those two surfaces, assuming they still have the same coefficient of kinetic friction and the same normal force pushing them together. So as soon as those surfaces are sliding past one another, that force of friction will be equal to mu k times n. So if we look at solving for mu k, we're going to quickly see that it's Fk divided by the normal force. And so this time we're going to have 6.1 newtons divided by 15 newtons. Once again, the newtons cancel out, and our answer will not have any units. And this time we get a value of 0.41. And so what we notice is that for that same brick and that same table, mu k is less than mu s. And that's always true for any two given surfaces. The value of mu k, the coefficient of kinetic friction, will always be less than the value of mu s, the coefficient of static friction. And so basically what that tells us is that it's a little easier to keep two surfaces sliding past one another than it is to get them to start sliding past one another. Think about why that might be, and we'll talk about it when I get back on Friday.